Okay, hi folks. Welcome to session SEC 342, Threat Modeling as Code, transforming your threat statements into attack trees. My name's Danny. I'm a principal security specialist with our organization that's called AWS Industries. I'm directly customer facing, so I get the opportunity to work with customers to understand specifically more around some of the application and security problems that they may be having, how to deploy that into the cloud, but also some of the principles around application security. Threat modeling being one of the biggest ones that we tend to talk about, or that I talk about with our customers. I'm joined here today by Christian.
Hi everyone, my name is Christian Leo. I'm a data scientist in AWS Security, mainly specialized in compliance automation and building and training AI model for security.
Yeah. So, threat modeling. Who here has heard of the 4-question frame or framework of threat modeling? Okay, a couple of hands. So really when we talk about threat modeling, this was a framework that was kind of coined by Adam Shostak in the late 90s of this mental model to help us define and think about and kind of structure how we work through the process of threat modeling. And it really comes down to 4 questions. What are we working on? What can go wrong? What are we going to do about that? And did we do a good enough job? Now, these questions, when we step through them one by one, when it comes to an application, when it comes to something that we're working on, really helps us to define risks, controls, and understanding the potential threats to an application. Now, why do we do this? Okay? And when do we do this? So, when we think about the design lifecycle of an application, we can typically see threat modeling performed in the design phase. If we do that, that means we get to identify threats early, we get to iterate quickly on early designs, we get to do this in a way that helps us define the appropriate controls to help reduce risk as we start to get to the later stages. We can also see this further down the pipelines as well. The reason that we do this, even when it comes to the deployment mode and even the maintenance mode, is because things change. The threat landscape changes. You know, from one day to the next, something may have happened. There may be a new vulnerability. There may be a new threat actor group. There may be something in place which allows us to relook at our application, relook at the threats that we originally had defined, and then say, do those things still apply given the new context, given the new information that we have? The reason that we try and do this as early as possible is because the cost of defect fixes increases exponentially the further right we go. So that's why it's one of the main benefits of doing it early. We should be doing it often, as I said, as the threat landscape changes, but the earlier we can do it, the cheaper it is to add those mitigations. No one wants to get to the point where they're almost at the deployment phase, they're just about to hit the button to production, and something has happened and security says, hold on, we've identified a threat. This should have been fixed in the design phase, but it's not now. We can't get this out into production because it's too high risk. All right, so the earlier we can do that, the cheaper it is from an effort perspective, engineering perspective, and from a risk perspective. So that's really what we mean by shift left. But the reason that we do this as well is because it helps us to keep pace with risk. Right? We see that risk goes up as you get closer to production, or as you are in production, as you are in maintenance. Obviously, if you're in pre-production, it may not be public-facing yet, you may not be exposing anything to users, and so therefore the risk is lower. But as we get out there, as we put things out on the public internet, we start to see scraping of live applications within seconds. And so we want to be able to understand that. We want to be able to have those threats in our minds, have the appropriate mitigations in place to help reduce that risk. Now, what are some of the benefits that we do this? The top one is my favorite. Whenever I do threat modeling workshops with customers, we always bring in business, we always bring in developers, and we always bring in security into the same room. How many times have those 3 different personas been in the same room together in your organization? Not that many. It would be great if we could have that every single day and they could be having active participation together. But actually, when you get to a threat modeling workshop and you're doing something on a whiteboard, that allows us to start building strong relationships. The business understands risk. They have certain decisions or certain criteria as to why things can go out into production or what risk they're willing to accept. The developers understand the application. They understand the code, they understand the intricacies of the workload. And the security understand the risk, they understand the threats. By combining those separate and kind of unique perspectives, it gives us a really powerful threat modeling activity. When we run this as well, we identify often similar types of threats, similar types of risks, and there could be controls that apply to all of those things that help reduce that risk. And so when we think about this and when we do threat modeling and we identify potential threats, there could be controls that are often overlapping. Let's say multi-factor authentication. That's going to help us to reduce a number of authentication type threats. And so where we say actually MFA is going to show up on 90% of the threats that we've identified, maybe let's start there, because that's going to give us a good return on investment, good value there. It also becomes very helpful when we want to adopt new technologies. If we want to adopt things like generative AI chatbots into our workforce, we want to understand the threats to that. What are the things that could go wrong? How can we quickly allow the business to adopt these new technologies? Because the developers, the people in that business, they want to use these things. So how do we, as a security organization, how do we allow them to do that fast, but safely and securely? And threat modeling is a great way to do that. And it also significantly helps us to reduce review time. At AWS, we do threat modeling as part of our application security review process. We have a program called the Guardians program, which is a set of builders that are specifically trained to act as security advocates on their team, and they help their teams do the threat modeling before they get assigned an AppSec engineer. And what we found is that where a threat model is applied and where a Guardian is involved, it reduces the time of an AppSec review by about 22-23%. That's a significant time saving. And so if you and your organization are starting to think about threat modeling and you want to do this early, the security teams, and you can go to the security teams and say, hey, we've done a threat model, we've identified a number of threats, and therefore a number of mitigations. That's only going to allow the security team to review it faster, maybe bar raise it a little bit, do some additional thinking and support and say, have you thought about these extra things? But really it's going to significantly reduce that time. So at a high level, this is the main framework that we tend to think about, at least that I speak to customers about. We've got our 4 questions. What are we building? That's our scope decomposition. We think about the scope. We think about our data flow diagrams. What can go wrong? We can think about threat intelligence input. That's really important to help us understand the current threats that are out there. What are previous known attacks from advanced persistent threats, from other threat actor groups? What are the techniques, tactics, and procedures they've used for certain similar types of workloads? And could those things affect us? We think about threat statements. We'll talk about threat statements in a little bit in a bit more detail, and we'll talk about attack trees as well. And then we do what can we do about it? We understand the risks. Is this particular threat to our application high risk? Is it high impact? Is it high likelihood? And we define those things. This is where the business lens comes into play. Why is it risky? Why is it high risk? Is it because it's going to compromise the confidentiality of our data, the integrity of that data, or the availability of the workload? Different applications will have different priorities for each of those. If you're just a public-facing site that serves content that is publicly available, maybe the confidentiality is not too high, but the availability is. Maybe if you're healthcare, then all of a sudden you're going to err much more on the side of confidentiality over availability. That then means we can identify controls. For each of the things that we've identified that can go wrong, how can we help to reduce that risk? How can we bring either the impact down or the likelihood? And then really importantly, we want to test the effectiveness of those controls. It's great to say, yes, we have this thing in place, but have we actually tested it? Have we gone through a penetration test? Have we done static testing? Have we done dynamic testing to confirm that we think that that control is sufficiently reducing the risk to a level that we are happy with? Super important. So, threat statements. Threat statements are a way, it's essentially just structured grammar. It's a way to write prescriptive threats, to make it iterative and to make them very useful. And the structure really helps us to define things like priority, and things like impact. So this is the main syntax that we'll talk through. A threat source with some prerequisites can do something, some threat action. That leads to some impact, which results in the reduction of a required property or goal of an asset. Now, a threat source can be an external actor, can be an internal actor. We've got different threat actors there. Prerequisites are just something that they need to have access to. It could be someone with no access, and that could be the prerequisite. Or it could be someone with administrative credentials or someone with access to the network. They can go and do something that's going to impact us in some way. Now, as I mentioned, the applications could have or should have a required property, like high confidentiality or high availability, high integrity. So when we talk about a threat that reduces that thing, that's where we put that into the goal, and then we have an asset. Is it an S3 bucket? Is it a EKS cluster? Is it something else? And so this syntax helps us to define, the structure of it allows us to do good analysis on things, right? Which of these, as you start iterating these over time and time again, you can say we've got 20, 25 threat statements. How many of those are internal threat actors? How many of those are external threat actors? How many of those impact the confidentiality or the integrity or the availability? How many of those impact this specific critical asset? So having this structure makes that analysis very easy to do. So let's talk through an example. An unauthorized user with the ability to scan for open ports can gain unauthorized entry to the application instances, which leads to crypto mining on those instances, resulting in the reduced availability of the application. Okay? So that first section is really the what can go wrong, right? Can gain unauthorized entry to the application instance. We then have the impact side of things, which leads to crypto mining, resulting in reduced availability. So that second section helps us to prioritize. But what we found with threat statements is they can go further. And we can do that in the form of attack steps. And it's great, the threat statement's really great to help us structure, to help us start thinking about the what can go wrong, but the attack steps are the how. How can that thing really happen? And it can happen in a number of different ways. This is a set of attack steps in order to get to that threat statement. They perform brute forcing SSH or RDP. They drop malware on the instance for local privilege escalation. They exfiltrate IAM credentials over DNS. They probe APIs with the credentials that they have, and they configure and create and launch UEC2 instances. And then they install crypto mining software on top of that. There could be 4, 5, 6 different other ways to execute and to get to the same threat statement. And that set of different attack paths is ultimately what we get to for an attack tree. Now, attack trees are nothing new. Bruce Schneier has been writing about attack trees since 1999, right? As a way to provide a formal and methodical way of describing the security based on a varying number of attack paths. And that's what Chris and I have really been thinking about. When I talk to customers about this, I'm thinking, how can we go one step further? How can we help them? How can we help developers start thinking about this thing? Developers may not necessarily have the expertise and the security mindset to think about all the different ways a threat statement can actually happen across their application. And so we have been working on a tool that we call ThreatForest. So this is going to be an open source tool. This is going to be something that is available on GitHub samples for everyone to go and use. And what ThreatForest does is it allows developers to execute this on the CLI in their terminal or in their IDE. It can point to a directory, and it will help run and create a set of threat statements and attack trees for them. We're going to demo this in just a minute because Chris, the brains behind the solution, is going to talk about all the science that has gone in behind this. But let me talk about the high level. The two main phases that we have are attack tree generation. This is gather some information, extract context from that information, and start the attack tree generation. And then phase 2 is the additional threat intelligence alignment. Now, this really becomes important to us because it helps us understand these things have happened in the past. They are linked to existing and known MITRE attack steps, and so they have really good resources, information associated with that. Known threat actor groups that have used that sort of attack step, known mitigations and controls that can help to reduce the risk of that attack step from happening. And so that's really phase 2. So diving in a little bit more, I'll let Chris go through the various phases and the science behind this.
Thanks, Danny. So let's zoom in on the first phase, the attack tree generation. What we built is a multi-agentic architecture that will start reading your repository. This repository may contain source code, architecture diagram, threat statements, and any piece of information that will help ThreatForest to actually automate both threat modeling and the attack tree generation. So we start with an agent that understands the architecture of your repository. It will start looking at what files exist, and it will guide the future agents. If a threat statement is provided, then a parser agents will actually analyze the threat statement. This can be a markdown file, a PDF, or this can be actually a file, an output of Threat Composer. Threat Composer is another CLI developed by AWS to automate threat modeling. If it's not provided, it will trigger instead a specialized agent to generate a threat statement file for you. The second step is the content extraction. So once we have an understanding of what this repository looks like, once we have a threat statement in place, then the agent will start gathering the evidence required to actually generate the attack trees. And then there is the third step, which is the actual attack tree generation. And so as a science person, I wanted to understand how we can leverage the domain knowledge of SMEs, security engineers, like Danny, like Anton, and other folks who contributed to develop ThreatForest, and science knowledge. And so this is where we implemented a framework called DSPY. DSPY claims to code and not prompt so that science and security engineers can collaborate together to define a basic prompt and then leverage science, especially this novel algorithm called GEPA, to create optimal prompts based on statistics. And what GEPA does is using genetic Pareto, genetic because it will spawn different variations of prompts and automatically using statistics find the optimal version. They won't be stuck on a local optima, but will find the very optimal version. And this requires SMEs to first create a first draft of the prompt, leverage Strengths Agent, which is an agentic framework that we use in production at AWS, and generate traces, so reasoning steps of the agent, the tool executions, input and output, and then have SMEs actually review those traces and score them and provide textual feedback that then GEPA will use to perform something called reflective prompt optimization. And this is an iterative step that we took, and we ran a bunch of times until we were satisfied with the prompt. The output of this is the actual final prompt. They will be visible in the repository. The second phase is threat intelligence alignment. Threat intelligence alignment starts with an attack tree that we generated in the previous phase. And now we want to match every step in the attack tree, every node, to techniques, to the TTPs, so tactic, techniques, and procedures. Specifically for the first release, we will be using the enterprise attack matrix by MITRE, which we pre-index as a graph, and then at inference time, once we generate every node in the attack tree, we'll be able to encode the node and retrieve the most similar attack step, technique by MITRE. And something important here, I don't know if you're familiar with embedding models. This is what we're using for the encoding, but they tend to be smaller than the classic LLM trained for text generation. And so one important thing when choosing the embedding model is that will the embedding model have knowledge about security? Because something that can happen is that depending on the choice of your embedding model, the embedding model may not have been exposed on security data. And if we are asking, does this attack step match a certain technique, you may get a random number. Why? Because the embedding model does not know what an attack step is, or you may get something very similar because it's recognizing that this is a cybersecurity domain. And so we are using specialized security embedding models. The default model that ThreatForest provides is AttackBird, which is an embedding model fine-tuned on the MITRE ATT&CK metrics, on security data and security knowledge. And to give you a comparison about why the choice of the embedding model is really important, we created this chart where on the left column you can see the attack step. These are attack steps that will be generating during the attack tree generation phase. On the middle column, we can see AttackBird, and the third column, MPNet, which is another embedding model for general purpose. Something that you can see from the scores, the similarity scores that are generated, is that they are different, even though we are trying to map the same attack step. And the third column, the general purpose embedding model, is less confident. It tends to generate a lower similarity score. Whereas the AttackBird is more confident with its prediction, which is what we want, because we optimize prompts of this attack tree generator to generate steps that are inspired by MITRE ATT&CK metrics or other enterprise attack matrices. And then the third innovation, we created our own local graph engine, and we are representing TTPs as graph, with the intent of, in the future, supporting multiple TTPs spanning from Wiz, MITRE, TTC, and so on, and merge them together so that we can increase coverage. And so once you want to actually match your attack trees to multiple matrices, you will be able to do it, considering multiple matrices at the same time. So now Danny will actually go through a practical example using ThreatForest CLI.
Okay. We're going to pray to the demo gods and see if this works. I'm going to need your fingerprint, sir, to unlock your laptop. Thank you very much. Okay, so now you press this button. Okay. It's a little off, but that should be okay. Right, so we're going to run, first thing we're going to do is we're going to run ThreatForest. Okay, so this is a CLI tool that we have here. It's going to set this up, and we're actually going to start this from scratch. Okay, so you can see the end-to-end process. For the first step is credential configuring. Okay, so when we do this, we at the moment for our initial release, we support Bedrock. We are going to support other LLM providers, Anthropic, Gemini, a bring your own API key type scenario. But for now, we're going to use Bedrock, and we're going to do that with an AWS profile. So we're going to choose our API provider. I'm going to hit Bedrock. We're going to choose a model. So our suggestions at the moment are to use something like Haiku for speed or Sonnet 4.5 for accuracy. Opus gives us more confidence and better structure, but it just takes a little bit more time as well. So I'm going to go ahead and go for speed for today. I'm going to go with Haiku. And then I'm going to use an AWS profile. If I can type correctly. I'm going to run this in Beast 1. And the first thing it's going to do is going to actually test our connection, just to validate that it can access the Bedrock service and it can access that model. So then what we have is our first step, which is to generate our kind of main workflow, which is to generate attack trees and analysis. And so in order to do this, it's going to kind of take us through. But we can see here on the configuration, which is just a YAML file that gets created, that we can see the Bedrock provider, we can see the model ID, we can see the region, we can see the profile that we're using, we can see the embeddings model that Chris spoke about, and we also see the TTP threshold. And so this is the threshold at which it will do that matching. So if its confidence score is above 30% or 0.3, then it will map that to a relevant TTP from the MITRE ATT&CK framework. This is configurable. If you want, you can say, actually, I only want ones with really high confidence scores, only map attack steps to MITRE if it's an 80% or above. You can go and actually configure that. But we're going to keep that as the default setting for now. And so what we do here is choose a directory, okay? Now, one thing that we have in this is, or one thing that we recommend, and the documentation as well that's in the GitHub repository talks about preparing your project. This is really important. Having good documentation. The more good information we can give ThreatForest about the application, what it does, what kind of things it serves, what its objective is it a healthcare application that's going to be public-facing and containing super high-sensitive patient information, or is it a static web page that is going to serve, just static content? The more context you can give it about the application as part of in your directory, right? And this is going to be local files, things like PDFs, MD files, images, anything like that. So it's multimodal. The more you can give it, the better the output is going to be. I'm sure we've heard this a number of times when interacting with AI. Context is king. It's very, very important to give it good context because you're going to get more accurate results. Yes, you can absolutely have no documentation or very little. It will still go through this process, but it will just give you more generic outputs because it doesn't understand the application as well. So I'm going to go over, in the GitHub, we're going to have a number of sample applications that you're going to have an opportunity to play around with. So in this case, this is actually, we're actually using the Threat Composer file. So Chris mentioned Threat Composer. Threat Composer is an open source tool as well that we've created to help you document your threat models. And what this does is it's got some application information. We've got a connected vehicle solution here. We've got an architecture diagram. We've got data flows. We've got assumptions. We've got an existing set of threat statements. We've also got a kind of another version of this data flow diagram here. Now, this is something that you as a developer can use day to day. This is using the AWS Toolkit extension in Visual Studio Code. You can go in and interactively modify any of these threats. You can go create new ones, and you can iterate on this directly in your IDE. You can then commit this, and it just lives as a living threat model in your project repository, and it can save in GitHub. You'll have the commit history as part of that. So we're actually going to go ahead and use this. So I'm just going to grab this path. I'm going to paste it in here. And then the next question that ThreatForest is going to ask you is, do you have existing threat statements? Okay. If so, press yes, and we'll continue on. If not, what ThreatForest does is it will generate threat statements on your behalf in the same syntax that we spoke about. And again, that syntax is so important to allow something like a model to understand that syntax, understand why it's important, and then use that syntax to create the threat statements, right? In a way that becomes easy to analyze. So I'm going to go ahead and say yes, because we actually have our Threat Composer file. So I can just copy the link to that file path here. And again, because it's Threat Composer, it just saves it as a JSON format. And then we are ready to go. So we are going to review the configuration very quickly. We've got our full mode project threat model. It's going to generate the attack tree. It's going to enrich with MITRE attack mappings and add the mitigation recommendations. So I'm going to go ahead and say yes. And so while this is working, hopefully it will go fairly quickly. And what we'll see is we'll see how this iterates through. We'll see the stages that it's going through. So the first one is actually looking at the Threat Composer file. It's quite a large file. This is where we've got the parser agents that Chris has mentioned, where we use that parser agent to look through the file to only get some of the specific things that it needs out of that. So in this case, the first thing it's doing is looking for the threat statements. So we can see here, it's extracted 11 threats. 6 of those are high, 5 of those are medium. Right? We can actually go back into Threat Composer on the dashboard, and we can see the same thing. Or high, medium, and lows, right? So 11 threats, 6 high, and 5 high, medium, or lows. Now, the next thing it's doing is going to then have our repository analysis agent look through that repository to get the context. So it's got some threat statements. It's going to look through the files, also look through the Threat Composer file as well for that additional context, and it's going to start generating the attack trees for us. If you want, in the meantime, we can actually look at logs. So in here, we can see two different types of logs. So we can see how things are going. And we can see that it's discovered in a series of files. It's got our threat model file. It's going to look through, identify the model provider, generate a number of threats, and extract the high priority ones. We can also look at strands to take a look at what strands is helping us do as part of the orchestration. So as we do this, the repository analysis agent has identified 12 different technologies. Lambda, API Gateway, DynamoDB has done this using the threat composer file and that architecture diagram. It's found 10 main data assets, so things like S3 buckets, EBS volumes, and 8 possible entry points. And so it's using that now to actually generate the attack steps. So as it goes through each of those different threats, so the 6 high severity ones, the next step is then the mapping. And this is where the embeddings model come in. We've got the attack steps in their raw format. It's now going to go through each of the nodes in that attack step and map it to the embeddings model, the attack embeddings model that is stored locally. And so it's going to map each one of these, and then it's going to generate the final output for us. So you can see that it's going through that, and then we can see what it does is it creates a nice visual dashboard for us, and it opens this up for us, okay? So we have, again, our exec summary, 11 total threats, 6 of which are high, 6 attack trees, 113 total nodes. The repository analysis agent gives us our project information summary here. It's a connected vehicle solution. It's a serverless architecture type. It runs on AWS. It's extracted the industry sector, and we've got a number of technology stacks in there as well. And now for the fun part. We have our high severity threats. So each of these threat statements, if you can see this, maybe I'll zoom in a little bit. Each of these threat statements have come from the threat composer file. So we can see that syntax. An internal actor with access to the AWS account can deploy a Lambda function that will use existing execution role, leads to unauthorized access to sensitive data, resulting in reduced confidentiality of registration status. Okay, so another threat statement using that syntax. And then we can actually go in and view our attack trees. So for each of these threats, I've zoomed out too far. Let me zoom in a little bit. Okay, there we go. So we can see this is where the interesting stuff happens, right? Our attack tree gives us a start point, which is our internal actor with AWS account access. That has been extracted from the threat statement. We then get down to a number of different ways in order, let me just zoom out for a minute, in order to get to our goal. And our goal down here at the bottom is confidentiality breach of the registration status. Now, from a visual perspective, we can see that there's a number of different flows in order to achieve this. Right? There's a number of different steps, attack paths, in order to get from our initial objective down to our goal. And we can click on each one of these nodes to look at what it's trying to do. So we've got reconnaissance, so it's looking at existing Lambda execution roles, identify sensitive data locations. If we follow this one down, it's going to enumerate IAM roles with excessive permissions, identify Lambda execution role, and each one of these, right, we've got deploying malicious Lambda functions. And so the point of this is that we've gone from a fairly broad, high-level threat statement, which is something bad can happen with the Lambda function, to a very specific targeted steps of how that thing can actually get executed across our workload. Which then means we can map that to MITRE. So we can see here, this particular one is 42% confident that it's mapped to this one. Now, obviously, it's trying its best, right? As we have more data that we're consuming, we can start to see this, the accuracy of these mappings go up. And then what becomes important is our mitigations, right? Because of this, we can now say, we can now look at some of the information that MITRE is going to give us to help, as a developer, understand why we need these mitigations in place. And now, as we expand this out, we can start to think about how many of these mitigations are common, how many of these things are, repeat themselves over different types of attack steps. Maybe we start there. going back to that benefit that I mentioned earlier of prioritizing controls and prioritizing mitigations. So that's really it from a demo perspective. I'll let Chris talk through some of the science and actual code behind some of this as well.
Thanks, Danny. So switching now to the actual code, some of the things that you want to look for and know when using this CLI application is that the first time that you're using it, it will create a .threatforest folder for you. It will generate a graph. The graph is stored as a JSON file with nodes and a relationship. The use of a local graph engine will make it a standalone application that doesn't need to rely on third-party applications or graph database. It's also much faster. The idea is that TDPs tend to be smaller in size, and so we don't need to rely on a proper graph database. This is also where we'll be able to see the embeddings that are stored. So every time that you choose an embedded model, they will automatically index every node for the TDPs. It will also create a .env file. I can actually show you the .env file here because I'm using the AWS profile, so it's not a sensitive information per se. But if you are using any other API key, it will automatically show it to you, so don't send it around. And the config YAML file where it can actually show what we're using, attack bird. You will be able to also set the TTP threshold. In this case, we're using 0.3. It's leveraging cosine similarity, so the score tends to go from -1 to 1. 0.3 is not necessarily low, but it's not necessarily high. But you can change that based on how confident you want to be in the mapping. And then a bunch of sample applications. Something that on code-wise I want to focus on is the actual modules. So the main entry point for this will be the CLI, but the actual core module will be the orchestrator, which is running all these multi-agent steps. But before diving into that, there is the graph module where we are using sentence transformers. So sentence transformers is a library built on top of the transformers library from Hugging Face. And what this lets you use is bring your own model. So you can use any model existing on Hugging Face. And now pretty much every open source model is on Hugging Face. And if you wanted to use your own model, for example, take these and fine tune it with your own data, you can do that. The next step is the graph builder. So this is our own logic for graph builder. Something that you can see here is that we leverage the MITRE ATT&CK in sticks format. And so we will turn every technique and mitigations into nodes. And one of the primary reasons why we're also using graph is that considering that we always want to do traversal, the complexity in when doing traversal from a graph is linear instead of quadratic compared to relational database. And this is our actual graph engine that will let us store. Behind the scenes, this is actually just using NumPy arrays and arcsort to get the most similar nodes, but then we'll probably make it a little bit more advanced as we scale up involving multiple graphs. And then this is the vector search function to run in-memory vector similarity search. We also have a visualization module, which is what lets you generate the report in HTML file. But now let's actually dig into the agent component. So something that I specified before is that we're using Strands agents. So if you're not familiar with Strands, it's an agentic framework developed by AWS. It supports multiple model providers. As of now, we have in experimental mode Gemini or Llama, LightLLM, Llama API, OpenAI, and Anthropic. And the content extractor relies on a base agent class and abstract class with a bunch of signatures, but its goal is to extract the context, and so we look for files and automatically classify them as architecture diagram, as README files, source code, and so on. And they will help. This agent has actually access to two different agents. One that is the parser agent, and the other one is the threat generation agent. The parser agent is used when we have a threat statement file or we have a threat composer file. And so it's instructed to extract existing threat statement from a threat statement file. The other one is the threat generation agent, which instead will leverage the information by the context extractor agent to create your own threat statement file. These agents are leveraging three main tools by Strengths agent. As Danny mentioned before, this is multimodal. It's multimodal because we use the read image tool by Strengths. This will encode images, and then it will automatically send a request to your LLM provider to reason it over the image. It will also be able to read files, list directories, and it's also using an editor tool to actually scan in your repository, create the 3 directory structures, run inline search, fuzzy search, so that if, let's say that you have a very big file that wouldn't fit in the context window of your agent, then it's able to run an intelligent search within the file itself. We actually run a smart tweak since the editor agent by Strengths is able to write and create new files. So we created a wrapper on top of it so that we can allow certain actions, for example, view to create the 3 directories and find line to start running a smart search. So that everything, when you're running ThreatForest, you don't have to run into the risk of actually overwriting your files or having it access something that you don't want to have it access to. Anything that once you select the path to the directory that you want to scan, the ThreatForest will only be able to read that directory, and it will only have read permissions. And then, just to continue, we have the 3 generator agent. The 3 generator agent is able to generate Marmaid code. So it's being prompt optimized on generating Marmaid, and then what we do behind the scenes is converting the Marmaid structure into a graph. And so this is pretty much it. The CLI module will actually be able to run the CLI, and it's responsible for the CLI interactions. And then models will contain the data signatures, and in utils instead we can be able to run the AWS validator and so on. In prompts, you'll be able to see actually the prompt that's been generated using DSPY with GEPA. In the future, we'll be able to release the specific module that we are using to run DSPY and how we can optimize with the intent that if you have a specific data set and specific needs and you want to customize ThreatForest to your specific data, you will be able to optimize the prompt and use the collaboration that I was talking about between scientists and engineers. Now, everything of this is available on GitHub. We made it available right before this talk. So, Danny, I think you have a...
Yeah, got a QR code. Cool. A couple of other things I think just in general that we could talk about for the last few minutes is some learnings that we've done. So one around the prompt is really important. When we first started creating this, it was a fairly big prompt, 1 or 2 big agents, a lot of reliance on the LLM to do a lot of the heavy lifting and intelligence, right? So it was a big prompt that says, you are a cybersecurity expert, read through all of my files, generate some threat statements, generate a series of attack steps, using that context. Whereas we found a lot of inconsistency. We live in a non-deterministic world these days, so we found it was hard to kind of get structure, get consistency out of this. And so that's why you see, we've got between 12 and 15 or maybe a few more very specific targeted prompts for very specific targeted actions and agents. We've got a number of agents, a number of prompts. This kind of small modularization of the prompting has allowed us to be very targeted and get very good structure and output and control the outputs of what we're expecting from the LLM, do some validation on that thing before moving on. Okay, so that was a really important thing that we started to learn through. Just a couple other things to show quickly is we also have the outputs of this is not just the nice visual dashboard in HTML that we've created, and we also store all of this data and provide all of this data in its kind of raw formats in MD and JSON. So this is the high-level report that gets created in an MD file. Right, so we see, again, a lot of the same information, technology stack, security objectives, analysis results, each of the high-severity threats. This is just the ID that comes from Threat Composer. And we have our generated attack trees, and then we've got our kind of recommendations here. And then for each, oops, let me close that one. For each of the attack trees, we then also, as Chris mentioned, format this in Mermaid. So it's a slightly different way of visualizing it, but again, slightly nice views, nice visuals here to actually get to this mapping. And then we see a little bit more detail on the MITRE attack mapping. We see the similarity scores, we see the mitigations in here. And then a little further down, we have some of that more attack path analysis. And then we also keep things in state, just in case there's any errors or anything like that. So, or if you do introduce new threats to your threat composer file, it will look at the state, understand there's one new threat, it's a high threat, we're going to go and create an attack tree based on that, rather than creating another 6 other ones that are that end up being duplication. And then the whole thing is then just stored in a large JSON format as well, in case you want to do anything more programmatic with this. Another example as well to show you, so we ran this one earlier. This is just one of the other sample applications that we have in the repository. This one didn't have any threats in here already, right? So we just had an overview of the application and an image that was used. And so this is kind of the other mode. This is the generation of the threat statements itself. And so we see here that it's actually gone through using this context and is generating threat statements for us. So in case you are at a point where you haven't started yet, that's fine. You don't have a threat model, we will help you create that threat model, and then this is used as input into the next stage for the attack tree generation. And then we can see here it's broken down using our syntax as well. Anything else you want to cover?
Yeah, no, just the emphasis also on the open source and local fact that we played out, so that most of the times if you are running a threat modeling, you want to make sure that nothing gets sent out on the cloud, or you have full control over your data. And so this is the reasoning behind some of our assumptions of having open source deployed in your own environment, running local embedding models, and reliance for the genetic component, bedrock that you can trust. And you having full control over the data, you can see the prompts and you can just see all the code. There is nothing that is not visible in the GitHub repository.
Okay, so wrapping up a little bit, just an overview of where kind of ThreatForest, or the coverage that we have, mapping back to our framework, okay? It can do everything apart from actually test the controls for us and do the risk analysis, right? So we are allowing it to help with the scope decomposition, or really the what are we building. To be fair, ThreatForest isn't really doing that for us. That's a you job, that's a developer job that has to create the documentation to give us that information. Again, the more we can give it, the better context we can give it with that scope decomposition, data flow diagrams and whatnot, the better you're gonna get, or the better output that you're gonna get. But we have our threat intelligence input. We've got a MITRE attack framework, right? In our next version that we're gonna be releasing, we're gonna have additional input from the AWS Threat Technique Catalog. If you haven't seen that, go check that out. That is specific steps related to AWS TTPs, so tactics, techniques, and procedures, that are also mapped to MITRE, but these are very specific to tactics used that we see, or our customer incident response team, the CERT, they see being used in AWS environments, right? So it's very, very specific to AWS environments. So that is a really, really great resource that we're going to be consuming as well. And then any other third-party open source matrices that are available, we're going to start to consume those as well. We've got our threat statement creation, we've got our attack tree development. Now, attack trees can also be used for other things, right? I've been thinking about this more and more as we've been creating this. Initially, this started out as we want developers to be using this, and we absolutely do want developers to be using this. We're trying to make it as friendly for them to use in their IDE, to use in their CLI. Another really interesting use case of attack trees is scoping and defining test cases for penetration testing and automated penetration testing. We're starting to see more agents in this space. We announced one in public preview yesterday, our AWS security agent, where it can do penetration testing against an application. And so as we're starting to see those, there could be really interesting overlaps where it takes some specific context of your application, generates the threat statements, generates the attack trees, and then that can be used as inputs for another agent to start simulating those attack trees on our behalf. Okay, so another pretty interesting use case as well. The other use case that I've been thinking about is from a defensive side. If you're a security operations center and you're a defensive organization, you want to maybe think about generating these attack trees, and then looking through them and saying, which ones of these would we be able to detect? Do we have the right logs in place to look for Lambda execution role bypasses or compromises, or the misuse of those? Do we have the detections in place to look for these types of things and these very specific attack steps? Do we have the logs in place? Do we have the detection use cases? Do we have the alerting? Do we have the runbooks? So it could be really interesting ways to stress test some scenarios for your defensive blue teams. That threat intelligence really kind of helps us to bridge the gap with how, okay? So we see that these industry frameworks are there because they are a collection of known attack steps, right, from known threat actor groups. So that gives us some understanding that these things are viable. They have happened in the past. There are certain threat actor groups which typically use these things more. That, again, allows us, if we're in a more defensive mindset, we may be able to say, given our industry, given the types of, our position in the market, we are usually susceptible to attempted attacks from these sorts of threat actor groups that are known for targeting these sorts of industries. We can go and simulate these, particular attack steps based on, known MITRE attack steps. And then the graphical side of things, right? As in through graphs. These knowledge graphs allows us to capture these relationships in a really structured way, right? And so having these TTPs as graph, which is just a more scientific way of calling an attack tree, means that we can start to normalize and start to understand the different ways these things are going to interact with each other and the relationships between them. And having those relationships between them means that it helps us to improve accuracy when we're mapping to the MITRE attack framework. And so, as Chris mentioned, we are happy to say that ThreatForest is available on AWS Sample's GitHub as of today. So that QR code should take you straight there. We encourage you to use it, clone it, play around with it, look at the code, run it, give us feedback. We really want to hear feedback from you, and you can connect with us through a GitHub issue or even via email. We want to know how it's working for you and what you'd like to see. Okay, so that's available there on GitHub. We recommend starting with the sample applications. Right, there's a lot of good documentation in there. The sample applications are there to help you test so that you don't have to test it on something that you may be working with. We've got links here as well for an overview of GEPA, that the framework that Chris mentioned earlier for our reflective prompt optimization, and obviously we've got the MITRE attack framework here too. Any closing remarks?
Just stay tuned because we'll provide many updates. We may release the research and the science that get into creating ThreatForest and also following up with specialized embedding models as well.
Okay, thank you everyone. Please fill out the survey in the app. Hope you enjoyed that. We'll be around for some questions as well.